How do you choose the right model? It's going to jump right to number 3 here. Does it provide sufficiently accurate predictions for the given application? My experience, I mean, let's put it this way. You can match anything if you have enough parameters, right? You can imagine you could create the most complicated constitutive model ever. It's got 100 parameters in it, and you can match whatever crazy behavior you want. In general, that's not useful because nobody knows what the 100 parameters are. So what you really want to do is get the simplest possible model that will match the observed behavior. Use that, or even start simpler than that and add complexity. So in theory, when you're doing these types of things, it's always not a bad idea to just start with elastic, because you set up your boundary conditions, you set up your initial stresses, you run this thing elastically, it's always going to solve. Right? I assume you talked about solving already. But you say solve, and if it's elastic, it should always solve. Nothing fails, right? If it doesn't solve, then you screwed something up. And you can go in and look at it and see if the results make sense, because the stress is always proportional to the strain. Everything should make sense. And it runs fast. The next step, what most people would do is run a more Coulomb model. So then you just need a cohesion and a friction. Stick that in there, maybe a tension strength. I'll get to that in a minute. Run the more Coulomb model. And again, it's not a lot of parameters. It's fairly intuitive behavior. See if everything's making sense. And then you start going and adding complexity from there. So if you're a soils person, you're probably going to go to cam clay or plastic hardening. If you're a rock person, you're probably going to go to hook ground, something like that. Okay, I've got one slide on plastic hardening. I will attempt to put something else together on this. I suspect I can just steal slides from FLAC2D course. The plastic hardening model is popular for this reason. With more Coulomb model, let's pretend you got something under stress. You've got initial stresses. And remember you did this thing where you set the displacements back to 0 after you solve for the initial stress. So you solve, let's say you've got this situation here. Solve for the initial stress. You set the displacement back to 0. Now you start excavating something. In a regular elastic material like more Coulomb, the unloading occurs in the same way as the loading, right? That's sort of the definition of elastic, right? You load it up, some relationship between stress and strain, and you unload it, and it's the same relationship between stress and strain, right? It behaves elastic. That is not realistic in a lot of cases for soil, right? For those of you that know about soil, probably most of you know more about soil than I do. Once these things have been squashed at some level of consolidation, unload them. They're actually stiffer in unloading than they are during loading, right? So if you use a regular old more Coulomb model, you get these blue curves where you're getting too much deformation in the unloading direction, right? It's behaving elastic. In reality, stiffness is now less in the unloading direction. And so the plastic hardening model accounts for that. Essentially, the fact the act of squashing it in the first place causes it to behave differently when you unload it. And so you get much more realistic behavior in these soils type of problem. And that's it in a nutshell. And we can go into the details maybe on Wednesday if I can find the slides. So that's kind of the background stuff. Now, how do we actually use them? I'm going to talk a little bit more about how we actually use them, and then we'll just pull up some FLAC examples and play around with them. Just so you can see how it's used. So this slide is actually slightly out of date because you can assign models and properties with commands. You can assign models and properties with fish. You can also assign models and properties with the model pane by clicking on something. Dialog pops up, fill it in. You're the kind of person that likes to use GUI-driven applications. You can do that with the constitutive models and the properties. And that's pretty cool. On point number 2 here, you can actually set it up so that the properties change. The fun part about using fish, this is really one of the reasons that you would use ITASCA software. Is you have this fish capability for Python, and you can do crazy stuff like assign different distributions of properties. So, changing properties with depth or some randomness or whatever crazy distribution you want, correlated random fields. I don't know, who knows, right? And also set it up so that the properties change as it's cycling, which is kind of cool. And people do that. So depending on certain things, stresses or whatever, you can actually change the properties as it's going along the cycle. You can do that with fish. Number 3, the user has a lot of power and flexibility when it comes to the behavior of these things, like softening, for example. So you remember I showed that curve of the strain softening, where the stress decreases after the failure. The shape of that curve you can actually just create with a table. So if you want some crazy curve there, you can just put that in. These things are possible. So the command would just look like this: zone C model assign to the name of the constitutive model. In this case, Monco. I apologize. This is actually a 3D example. If you look at the gray, you can see all the commands are actually 3D commands, but the constitutive model assignment is exactly the same. Zone C model assign, whatever name you want to give it. And the properties, again, exactly the same as 3D. Zone property, name of the property, value, name value, name value, name value. One of the weird things about ITASCA programs is that there are no units, or at least you don't specify the units when you start. So if you've used rock science, when you start a new project, you say, oh, I want to use kilopascals, or I want to use pounds per square foot, or whatever. Probably Plaxis does the same thing. I haven't used it. The ITASCA world, you don't specify the units. You as a user just have to be careful that you're using a consistent set of units. So for example, in this case, it looks like it's probably pascals. And when I'm doing this myself, I always leave myself a little comment. You can give with a semicolon and say, I'm using pascals. So consistent set of units, this is out of the manual. You just need to go down one of these columns. And in a nutshell, what it really means is, I mean, probably in the metric world, you're always using meters per minute. That doesn't change. The imperial world, you're always using feet per minute. That doesn't change. You've got a bunch of properties that require stress units, so like cohesion, initial stress, things like that. So that's where things get different. So you can have, in the metric world, you probably want to have pascals, kilopascals, or megapascal. A lot of the examples in the manual just use pascals. If you're a soils guy, kilopascals might be useful. If you're a rock person, megapascals might be useful. If you're a mining person in Nevada, pounds per square foot is useful. So it's relatively easy to make sure that you put all the stresses in the right set of units. The only other trick is then to be careful with the density. So if you're using pascals, your density is just kilograms per meter cubed. So it's going to be something like 2,000. If you're using kilopascals, you got to divide that by 1,000. So now your density is going to be something like 2 megapascals divided by a million. So now your density is something like 0.002. In the imperial world, the density is this weirdo slugs per cubic foot. And it's probably going to be something like 5. There you go. And then I'm sure you talked about this already, but worth repeating that in the ITASCA world, compression is negative. Compressive stresses are negative. And I can almost guarantee that this will trip you up at some point, especially when it comes to plotting principal stresses. They say, oh, I'll just plot the maximum principal stress, thinking that's going to be the maximum compressive stress, but it's actually upside down. You want the minimum stress, because that's the most negative and the most compressive. Okay, and all these things in the document. If you're looking for, I'm just going to click on it. If you're looking for the details about all these constitutive models, they're not listed under FLAC. So here's your documentation tree, right? Got a FLAC section. Constitutive models are actually into this general ITASCA software guide section. Because they're used by FLAC, they're used by FLAC2D, they're also used by 3D. The same constitutive model. So things that are used by more than one software program are in this general section. There you go. So if I open up the constitutive models, I've got null, I've got elastic, I've got plastic. So here's all the crazy plastic models that we've got. There's all these Crete models. And there's a bunch of actual tests and verifications. And most of these tests are like fairly simple one zone tests just to show you different behavior. But they're pretty useful to look at the test just to see how to use these models. And if you click on one of these things, the most useful part, of course, is figuring out what the properties are called. If I click on more Coulomb, every one of these documentation sets has a table with all the properties listed. There we go. Right, so it's just a list of all the properties that you can set. This is, you may or may not be interested in all the math. If you're a student, you're probably interested in the math. If you're a practicing engineer, you probably don't care. So you scroll down here and then get the list of properties. Good to go. Okay, this is basically stuff we already done. Oh, but one thing here in bold, which is worth mentioning. If you change the constitutive model of a zone, we're going to do this in an example, so you don't only have to pay attention now and you'll still be fine. If you change the constitutive model of a zone to something else, you have to reset all the properties. So for example, let's say you have an elastic model. You set the Young's modulus, the 1E7, Poisson's ratio to be 0.2, and you run some steps or whatever. Then you flip it to be more Coulomb. More Coulomb also has a Young's modulus and a Poisson's ratio. But because you change the constitutive model, you need to set that again. So you just have to be careful about that. And it's pretty hard to go wrong, because if you don't set the Young's modulus, it's got zero stiffness and it doesn't work. It actually gives you a warning and says, I have zero stiffness. So you're not going to make a catastrophic mistake here, but I'm just